This lecture considers the easy diffusion model in its application to something called the speed-accuracy trade-off, which is a foundational phenomenon in the study of speed decision-making. We're going to use data from a recent experiment by Grange 2022, their experiment 2, which studied decision-making, and they were interested in depressed versus non-depressed participants. We won't look at that. We'll just look at the basic task and the instructions they gave people to do in the task. You can see the task here. It involves originally you fixate on this cross, and then you're shown a face that has eyes but not a mouth yet. And then you're shown the mouth. And this is an example of a short mouth because the mouth is entirely between the eyes. It would also be possible to have a long mouth here. Then the mouth is removed, and participants have to make a decision saying whether it was a short or long mouth on every trial. So that's the simple two-choice decision that they're making on every trial. Before Grange ran the full experiment, they ran a pilot experiment with 50 prolific participants recruited online, really as a manipulation check for the two sorts of instructions they wanted to give participants in terms of how they should go about answering these questions. One was what's called an accuracy emphasis, where people were told to be as accurate as possible without taking too long. And so if participants made an error, they saw a big incorrect message to remind them that they should be taking the time they needed to get these questions right about the long or the short mouth. Another set of instructions that you could have as you did the task was a speed emphasis, to go as quickly as you possible, but don't make too many mistakes. So you're not just guessing, but you're trying to go as fast as you can. And now participants were warned if they went too slow. So if they were slower than half a second, they were told that's too long, and therefore encouraged to go faster. So they're emphasizing speed or accuracy both in the initial instructions and in the feedback that people are getting throughout. So each participant did 8 blocks of 48 trials, and these blocks alternated between speed and accuracy emphasis. So you might do 48 blocks trying to go as fast as possible without guessing, and then 48 blocks being as accurate as possible without taking too long. For all of the participants in all the trials in these piloting data, 99% of the response times are within a tenth of a second and 1 second. So we're just going to look at those trials. In other words, we've excluded some outliers in the analysis that you'll see now. So here's data from participant 8, and these show what's called the speed accuracy trade-off. So in the top, we have the speed condition, and the correct responses are shown in green by their response times. So somewhere between 0.2 something, and there's a couple that are up around 0.8, but most of them are within the 0.2 to, let's say, 0.5 range for the correct decisions. And then the errors that they made are shown in red. So you can see they made some errors in this speed condition. You can see the distribution of response times showing this characteristic rightward skew. Below is the accuracy condition, and again with correct decisions in blue and the errors again in red. And so you can really notice two things here, that people went a little faster in general in the speed condition. These response times are generally smaller in the green than the blue, for example. And that people made slightly more errors, slightly greater number of errors in the speed condition. So there's a few more of these red dots. There are very few of these red dots in the accuracy condition. And that's the speed accuracy trade-off, that when you tell people to go faster, they can go faster, but they make more errors. If you tell them to be more accurate, they can be more accurate, but they take longer. So there's a trade-off between speed and accuracy. You can be fast or accurate, but not both, if you like. So we can apply the easy diffusion model to those data to each of the conditions separately. That is, we get drift and boundary and non-decision time parameters for both the speed condition and the accuracy condition by independently applying the model to each condition. Here's what we get. For the drift rate, here's the marginal posterior distribution, and you can't even see the speed one because it's underneath the accuracy one. So exactly the same drift rate for both conditions. For the boundary separation, there is a difference. There's a shorter boundary, a narrower boundary, a tighter boundary, if you like, for the speed condition than there is for the accuracy condition. So this lower value means people are being less cautious in the language of the easy diffusion model and more cautious in the accuracy condition. And then the non-decision time, again, very similar parameter values for both of them. And this is the classic diffusion model explanation of the speed accuracy trade-off. So the idea is that people's ability to move their finger to press the button or other non-decision elements of the response time, that doesn't change on the basis of the speed versus accuracy instructions. Nor does the drift rate, because the idea is that this is a property of the stimuli. This is however complicated it is to get information about the length of that mouth relative to the eyes by looking at the stimulus. It's a property of how the stimulus is drawn, so that doesn't change between the task instructions that are given to emphasize speed or accuracy. But the boundary condition is something the participant can control. This is how cautious they're being, how much evidence they need before they make a decision. So when they're told to go fast, they don't need so much evidence. When they're told to be accurate, they decide they need more evidence. And that explains this lower and higher boundary separation here, which in turn explains the pattern of data that we see. When there is a longer boundary, response times are going to be longer, but there's less chance of making an error. Here's another participant from those 50 who shows the same sort of pattern. There are some slight quantitative differences here, but the qualitative story is the same. Slightly faster in the speed condition with slightly more errors than in the accuracy condition, and that's explained not by the drift rate or the non-decision time, but by differences in the boundary separation. And see if we go back and forth that the boundaries are a little lower for both conditions for this participant. So this participant is a little less cautious overall, for example. It also seems, and this is smaller, but maybe their drift rate is a little higher. So one way to interpret participant 41 relative to the previous participant 8 is that they're able to get a little more information from the stimulus, but they're a little less cautious about things. But the key point is that the speed accuracy trade-off is being explained in this same way. This is the classic diffusion model explanation. It doesn't always work this neatly. If you look through all 50 participants, you certainly don't get exactly the same story for all of them. Sometimes this isn't really a property of the model, but just of the person and the data. So if we look at participant 50, there's not a lot of evidence here of a speed accuracy trade-off. There's maybe there's slightly more errors here, but a very similar number of errors and no real big shift in the response times. So if a person doesn't show a speed accuracy trade-off, the model won't detect it. And you can see there's quite possibly the drift rates and the boundary separation are the same for this participant in both cases. Different example where perhaps the model doesn't tell as clean a story as might ideally be liked is one like this, where this participant shows a much broader range of response times and shows many errors in the speed condition. Their data actually look a little unlike other participants, but they do show a speed accuracy trade-off. Many more errors here with faster responses, fewer errors here with longer response times. But the diffusion model parameter inferences don't infer it in the classic way. The drift rate in particular is different between the two. The boundary separation is as we would expect. The non-decision time was as we would expect. But one way to interpret this is the easy diffusion model's inferences is that it's not as simple as the stimulus didn't change and people just got more cautious, or this person just got more cautious. It's that this person actually gets less information out of the stimulus when they're in that speed condition. So something about that has changed the way in which they're perceiving the stimulus, not just the caution they apply to how much evidence they need before they make a decision. So that potentially provides some additional insight, but it's not the classic speed accuracy effect in diffusion model. The classic effect would be to associate drift rate with properties of the stimulus, non-decision time with properties of motor movement and low-level visual processing, and to associate boundary separation with the explicit manipulation of speed versus accuracy emphasis in making decisions.